Hello, dear students. So this is our lecture number 9th on these tensors. And in previous topic, we have discussed about these tensors. So today's topic is about that metric tensor, right? So metric tensor. So you may find that. So this topic, this metric tensor, it is central to our subject. So it can. So if you can, so there should be one complete this unit for this topic, that's metric tensor. So that is why some authors call this metric tensor as fundamental tensor also, right? And so before that, if we make now the coordinate transformation, if we make now the, we can write the coordinate displacement. If you write now the coordinate displacement dr vector, so you can write that dr vector will be equal to, so this will be equal to, so you are basically making the coordinate displacement. So here we need to make distinction between the distance and the coordinate displacement. Whether this distance is equal to the coordinate displacement or not. So that means we are making. So this is basically the coordinate displacement. You are writing the dr in terms of these rectangular coordinates. So that's x cap, y cap, and z cap, right? Now, similarly, so you can write this is basically for, if you write it in this rectangular coordinates, or if you write this dr vector, so in the cylindrical coordinates it will be, that will be that d rho. So that will be equal to that. That's r sin theta d phi. So this is basically you are writing these coordinate displacement dr, this distance in terms of these unit vectors in rectangular coordinates, or in these cylindrical coordinates, or you take these spherical polar coordinates, because these are those basis vectors rho phi and z in this cylindrical coordinates. And similarly for the spherical polar coordinates, we have that r theta and phi. So it is very clear. So this is basically so how you can make transformation from some distance to some coordinate displacement. You are basically displacing the coordinate system, right? So this is very clear now. So if you write now here, if I write here this dx, so if you make coordinate displacement here, so dr equal to dx, because dx is, so this is the distance, because this is simply the distance between the 2 points. If you are making a shifting from some x to x plus dx, right? So that's, if you make shift from some x to x plus dx, so that is our, so this is our dx. Right? So this is simply the distance, right? Now, similarly, we have this. These are, so for rectangular coordinates, it's okay, but for the cylindrical coordinates, so this, if you talk about now for cylindrical coordinates, so d phi is not equal to distance, right? So d phi doesn't have the dimensions of that distance. So that means you need to multiply some rho into d phi, right? So you need to multiply by that this rho. Rho is simply the radius of that this vector. So that's the radius. Uh, because when you multiply this radius to this is simply the angle, right? Then this has the unit of that distance, because this is equal to, because this has a, because the radius you are taking in terms of that length. So then rho d phi becomes equal to the this units of distance, right? And similarly, if you write for this, similarly for this phi, or for this in case of cylindrical coordinates. So d phi similarly, so it doesn't have the dimension of that length, units of distance you can see. So you need to multiply by r sine theta to this thing, right? Then it can have the units of distance, right? So this is so let us come to that point. So why we basically introduce this metric tensor? So we'll come to that point, right? Now, if you write now, simply if you calculate now ds square, because if you write now ds square, that is equal to, right? So that means square of the distance. So it is, when you take square of the distance, so it is always positive because you are taking mod of that. So this is always positive. Now, if you write now that this is equal to dr dot dr, right? Or you can rewrite this as, so ds square will be equal to, right? So this is clear in this rectangular coordinates. So because this has the this units of distance here, right? So for rectangular coordinates, okay. Now if you talk about now for cylindrical coordinates, so for the cylindrical coordinates, we have ds square should be equal to, it is some that 0 square uh, that is, okay. So that means here simply when you multiply this, when you write the ds square is simply dr dot dr, right? When you multiply here, so you need to multiply wherever you will find phi, so you need to multiply it by some units of distance. So like we have this d phi here, so d phi को हमें क्या करना है, you need to multiply it by rho square, then it has units of distance. Then we can say that ds square, this right hand side equal to this left hand side is equal to right hand side, right? And similarly for this one, because dr has a units of length, right? But this d theta, so this is simply the angle, right? So it doesn't have the units of length. So you need to multiply this theta by r, okay? And similarly, when you talk about this phi, so that's also the angle. So you need to multiply it by r sine theta, right? So this is what I wrote here. So this should be r square. So that means you need to multiply r square to this term and r square sine square theta to the third term in spherical polar coordinate, because these are in rectangular coordinates, these are in cylindrical coordinates, and these are the spherical polar coordinates. Spherical polar coordinates, right? Okay. So that means I can write here. So why I'm writing this thing? Because I need to write that when you make the coordinate transfer, as I already told you. So is there any distinction? So when you make, so this, so you can say that this, so you can make a distance between the distinction between the distance and the coordinate displacement. So this is simply the square of the distance, and this is simply the coordinate displacement, right? So that means they should be equal, right? Okay, so but in different coordinate systems, so it should remain invariant, because length element it remains invariant. So that this ds is simply the length element. You are basically taking the distance between the 2 points, and that distance should remain invariant if you make transformation to some new coordinate system, right? So this is what I wrote here. So you need to multiply it by some factor in order to make it the units of length, right? So this is what I wrote here, right? So why I'm saying these things? So this metric tensor basically, this metric tensor helps us to write it in some compact form, right? So I can write some compact equation to all the three coordinates, right? So it depends upon the value of that metric tensor, right? So let us first rewrite this term as, so I can write here, suppose our x1, okay, so let me write here, suppose x1 equal to x, okay. So that means, so this is, so that means our x1, तो अगर मुझे ये देखना होगा किसमें, So if I write these coordinates x1, x2, x3, this rectangular coordinate system. So this will be simply that it will be that x, y, and z. And similarly, if I write this x1, x2, x3 in, so this is in the rectangular coordinates. And similarly, if you write this in that cylindrical coordinates, so in cylindrical coordinates, so this x1, x2, x3 will be, it will be that rho, y, and z, right? And similarly, if I write this coordinates in this spherical polar coordinates, so this will be uh, so this is in spherical polar coordinates. So that means I can write these, or you can write these are simply those basis vectors, right? And these are you can write if you write for different coordinate systems. So for rectangular we have this one. This is for cylindrical and this is for spherical polar coordinates, right? Now, so if I generalize it, because as I already told you, our ds square should remain same, right? So I can write now. If I write now, what's our ds square then? So this should be some. So it should be simply the multiplication of those radius vectors, right? Or you can write this as, so this will be that d r dot dr, right? Or you can rewrite this as, so this will be equal to, okay. So I think it's clear because I will take values because I can take values that, so you can write that I can take values that 1, 2, and 3, right? So that means if x, if it is dx1, so this is dx, and if it is dx2, that is dy. In rectangular coordinates I mean to say, अगर हम rectangular coordinates की बात करेंगे, so for different values of that I equal to 1, 2, 3, so that corresponds to our dx, dy, and dz component, right? So that means if I take all possible values here, so if I expand this, so gives the values of this I and j, because uh, I I runs from 1 to 3. So 1 corresponds to first x, y, and z coordinate, and similarly for g, right? So that means I need to take all possible combinations, right? So, but if you write this as, so this will be equal to that dx1, dx1. Right? So all possible combinations. So यहाँ पे हमें all possible combinations, right? So if I write here, so this will be equal to, so first one because our x1, so if you check that this one, so this x1 in a rectangular coordinates corresponds to x, x2 corresponds to y component, and x3 corresponds to z component if we talk about rectangular coordinate system, right? So that means I can rewrite this as, because so dx1 will be dx into dx. So all possible combinations. So my the main reason is why I wrote it in this form, because there may be some more terms involved. So but so we can have, तो यहाँ पे और भी terms यहाँ पे होंगी, that is dy square and dz square, all also other possible combinations. So but this doesn't hold, because our ds square is equal to, it should be that dx square, because our ds square should be equal to, so it should be equal to that dx square plus dy square plus So it should be equal to this one simply, right? But what I am getting some cross terms here. So some dx into dy, right? So this term, so this is not valid. So that means I cannot write that ds square. I cannot write that ds square in terms of that dxi into dxg in this, right? Because I'm getting some cross terms and I'm not getting this result because I should get that ds square should be equal to this, right? Because simply you are taking multiplication of lengths, right? So that will be equal to this, right? So what I should do here, I should introduce here some matrix, or you can write similarly for this cylindrical coordinates. You should get that is d rho square plus rho square d phi square plus dz square, right? And if you write that in this the spherical polar coordinates, so ds square should be equal to that dr square. So I should get this, right? So I need to check because I am writing that मैंने यहाँ पे लिखा कि that square of the length element that ds square I can write it in some compact form. But by writing this ds square in this fashion, so it doesn't work. So it doesn't work. So that means I need to introduce something in order to get these results. So that means ds square should be equal to this one. ds square in the cylindrical coordinate should be this one, that is d rho square plus rho square d phi square plus dz square. And similarly in cylindrical spherical polar coordinates, I should get that dr square plus r square d theta square plus r square sin square theta d phi square, right? So I should get these ds square in different coordinate systems. So for that, so I cannot write ds square in this manner, right? So what should we do? So we write now. So we should write now. So if I write here now ds square as, because if you write this as, so I can write this as ds square as, so I can write it this way. So that means this dxi and I and j will take those values 1, 2 and 3. So that means we can get that I equal to that I starts from 1, 2, 3. So that means it will be dx dy dz. And similarly, if you talk about the cylindrical coordinates, it will be rho phi and z, right? Because you can write that. So if you remember that, so in this one, right? So what I wrote here, so x1, x2. So in second we should get that rho phi and z, and in this we are getting that r phi and theta and phi. So for that case, so in order to generalize this, so I am introducing now this g of ij, right? So this g of ij. Now if I expand this now, तो पहले मैंने expand जब किया था, so when I expand it earlier, so I am getting some cross terms, so I am not getting these results, right? So ये results मैं नहीं ले रहा हूँ. So that means I am writing now in some new fashion. So that is what I wrote here. That is ds square is g of ij dxi dxg. So let us expand this. So let us maybe later we will see the what is the significance of this GFIG. So there is some quantity, some scalar, so we need to check it out, right? So before that, so let's expand this term. So we'll expand this as, so this will be equal to that. Right? With that, this GFIG. So in this, if you talk about this in a rectangular coordinates, अगर मैं rectangular coordinates में लिखूंगा, so the form of this will be 1 0 0 0 1 0 0 0 1. So that means this is the 3 cross 3 matrix. And if you, तो ये मैंने क्यों लिखा इस form में? So I'm basically putting it by hand in order to write that ds square in some compact form, right? So I should get that ds square equal to that dx square plus dy square plus dz square, right? तो उसको लिखने के लिए I need to introduce some matrix here g of ij, so that I should get rid of those off diagonal elements. क्योंकि आपने यहाँ पे देखा कि I'm getting some off diagonal elements here. So you just observe. So I'm getting some off diagonal elements. तो उससे क्या होगा? So I cannot write that ds square in this form. तो इसको इस फॉर्म में लिखने के लिए so I'm writing that this matrix G of ij, which is called which is called that matrix tensor. So I am writing that the value of this should be some unit matrix, right? So that is 100. So that is why. So if you take now the off diagonal element, so that means अगर मैं और term यहाँ पे लिखूँगा plus I can have that one by g of 1 2 also. So that is dx1 dx2. Right? And some more terms. तो यहाँ पे और सारी terms आएंगे यहाँ पे, right? But what will happen to this term? Because so for this, so this is our g11. So this is g11, g12, g13. So this is g21, right? So that means जो हमारा g12 है, so g12 is this one. So this will be 0. So that means this term will be 0. And similarly, if you write that g13, so g13 is this term. So this term is also equal to, so 0 multiplied by this term, so it will be 0. Right? And similarly, if you take any off diagonal term, तो यहाँ पे अगर मैं यहाँ पे लूँगा ये वाली term, so sorry, so I should write it here. Right? So if I take that g13, so g13 is also 0, and this will be our g21. So this will be g22. This is g23, g31, g32, g33. So that means I should get only those diagonal elements that terms will survive here. So ये term cancel हो जाएगी. This will be 0, this will be 0. I am getting only these two terms. Right? So that means I can write that. So this is the form of the matrix. Right? So I should get here. So this will be that g11. Okay. So this is simply that. So g11 is 1. So this will be. Okay, because this should be equal to 1, this is equal to 1, this is equal to 1. So I should get the dx square, dx into dx, dy into dy, and dz into dz, right? So I should get this thing. So this is for if you write that, so this is the form of matrix, and this matrix is called, that matrix tensor, or sometimes it is called that, you can say that, this is called a fundamental tensor also, right? So this is the fundamental, so because you can find it everywhere in these tensors. When you use this tensorial approach, so you find this matrix tensor everywhere, right? And you will see its significance in general relativity also, if you talk about the special relativity, right? Now, so this will be our that ds square here, right? So if you write now this ds square in that cylindrical coordinate system, so in cylindrical coordinate, so if you write that, so let me write it here. So in cylindrical coordinates, so you should get that ds square will be equal to. So what should I get here? So यहाँ पे क्या आना चाहिए? Because that ds square should be, because ds square is, that is 0 square तो इसके लिए जो हमारा मैट्रिक्स होगा, okay, so that will be different for this one because I am using the different coordinate system, so that's cylindrical coordinates, right? So the form of the matrix here, so that form of the matrix that I wrote here, that G of ij, so that will be equal to, okay, so I am multiplying it by row square. मैंने आपको already बताया क्योंकि it should have the units of length, so that is why you are multiplying that row square to our that second, that is rho square, that d phi square, right? Because phi is basically it's the angle, so it doesn't have the units of length. So that's why I'm multiplying here by rho square, right? So in order that it should have the units of length, right? So the form of this matrix answer will be of this 1 0 0 0 rho square 0 0 0 0 1, right? So that means this will be written as, because g11 is 1 here, and this is dx into dx is, that is d rho into d rho plus, okay, so this is our ds, right? And similarly, if you write for cylindrical coordinates, so cylindrical coordinates में हमारा ds square क्या होना चाहिए? So that is dr square plus r square. Okay, so that means जो हमारा मैट्रिक्स यहाँ पे होना चाहिए किसके लिए? cylindrical coordinates, spherical. So for spherical polar coordinate, or that, okay. So this should be there for this. If you write for this for spherical polar coordinate, तो यहाँ पे जो हमारा G33 होगा, that will be r square sin square theta, because this makes us, because by multiplying by this r sin theta or r square sin square theta, it makes it the uh, units of length, I can say, right? So similarly, for second, this is G22 is r square and G11 is r square, right? So this matrix, and it is different for different matrices in order to get that units of length. If you make transformation from some distance to some coordinate displacement, displacement to some coordinate displacement, right? Distance to some coordinate displacement, okay? So, and the form of this fundamental, that tensor is different for different coordinates. So for cylindrical, I have this one, and similarly, अगर हम cylindrical spherical polar coordinates के लिए लिखेंगे, it will be of this one, because I should get that ds square should be equal to this one, right? So that means जो हमारा g11 यहाँ पे 1 होना चाहिए, g22 should be r square and g33 should be r square sin square, right? So now you can raise a question. So where from we are getting these matrices? I am basically putting it by hand, right? So we can calculate them. We can calculate them with the help of these basis vectors, right? So I can rewrite now. So how to calculate now? So if you write now how to calculate, okay? So we need to calculate the components of this matrix tensor. So let us calculate for, because for this rectangular coordinate, so it's very easy. So let us calculate for some for spherical polar coordinate first, because for spherical polar coordinates, our R vector is simply that, R vector is that x square And what's our x here? Because x is equal to, okay. So let's use it here. So I simply write that x, y, and z in spherical polar coordinates. So that is r sin theta cos phi, r sin theta sin phi, and z equal to r cos theta, right? So let us use it now. Let us calculate now. So if I calculate now the basis vector, so we will calculate these basis vectors now. Basis vector. So what's our ER? Okay. So these are basis vectors, not unit vectors. So remember that. Okay. So ER I can write as, that will be that dr upon, or you can write this that is right, because we need to differentiate it partially. So you write now. So that will be equal to partial r cap r vector by partial, right? So that means you can write this as, okay. So instead of that r, you write that, okay. So this will be equal to, because you need to differentiate it by partially with respect to r. So this will be, so this is our ER. So because I need to calculate that, so the components are that metric tensor, right? And I need to, for that purpose, you need to calculate those basis vectors, right? These spherical polar coordinates. So that means you need to calculate that ER, E theta, and E phi, right? So we have calculated that ER is this one. And similarly, if I calculate now what's E theta, okay? I simply use that x r cap, y r cap. So x is the spherical polar, that's r sin theta, sin phi, r sin theta, r sin theta cos phi, r sin theta sin phi, and z equal to r cos theta, right? So I simply use that. Now we need to differentiate it partially with respect to theta here, right? So that means this will be equal to, okay, because so you need to differentiate this term here. So this term will be that sin theta cos theta and sin cos, and this cos minus sin, and rest is zero, because you need to differentiate it partially with respect to theta, right? And similarly, so this or E theta. Now or E phi will be equal to, so that will be partial by partial phi of r vector. So this will be equal to, so I will not write it because it will take more time. So better is to write, because you know what's r. R is this one. So this time अभी हमें क्या करना है? We need to differentiate it partially with respect to phi here. So this one. So first term will be that minus and second will be, so that will be equal to, okay, because, okay, so this is basically, I can interpret this. This is the relation between that basis vectors with the unit vectors also, because you find here r theta, so this is again term of x, y, and z. Right? Now you can make a transformation from some these rectangular coordinates to some these cylinders, this spherical polar coordinates. You can say, right? And you write now, so this E5 we have calculated. So if I write now the form of the matrix, so G of ij will be equal to, so that will be equal to that. It will be that ER dot here 0 0. Right? So that means इसके लिए हमें क्या करना है? We need to calculate that ER dot ER. And similarly theta with E theta, so that means ER square, E theta square, and E phi square, right? So if I calculate now, what's our ER here? Oh, okay, so let me write, so here. Okay, so let me write it here. So our ER square will be equal to, so that will be equal to, so we have already calculated what's our ER from here. So ER square is, so you need to multiply ER dot ER. So this will be sin square theta cos square phi. That is x dot x, x square dot x. So that's equal to 1. And similarly, sin square theta sin square phi. And here cos square theta, right? So that means this will be simply that sin square theta cos square phi. Right? So this was ER square. So if I combine this, so this gives me, because when I combine this and this, because this is sin square theta you take common, so sin cos square phi plus sin square phi will be equal to 1. So this will be that sin square theta plus cos square theta. So that is equal to 1. So that means हमारा जो ER square that's equal to 1. And similarly, if I calculate now E theta square. So let us go back. So what's our E theta square? So E theta square is from here. Okay. So E theta square. So what should I get here? So E theta square is this one. So that is r square cos square theta cos square phi plus r square cos square theta sin square phi plus r square sin square theta. So that means I can write here my this. So let me write it from here, so it's very clear now. So our, okay. So let me write it here now. So E theta square will be equal to, so E theta square will be equal to r square cos square theta cos square phi plus r square. तो अगर मैं इनको कंबाइन करूंगा, सो इफ आई कंबाइन दिस एंड दिस टर्म, सो इफ आई कंबाइन दीज टू टर्म्स, तो यहाँ पे क्या आएगा? तो यू कैन टेक दैट cos square theta out, r square cos square theta out, so this will be that. Because when you take that r square cos square theta out, so inside will be sin square phi plus cos square phi, that's equal to 1. So we'll get this one. So this will be equal to that r square. So that means जो हमारा r theta square, that comes out to be r square, right? And similarly, if you calculate now what's our e phi, square. So e phi square will be equal to, that will be equal to r square sin square theta So you just check. So you can check it from here. From which? Okay, so from here. Okay, that's okay. So if I is this one, so that means this will be r square sin square theta sin square phi plus r square sin square theta cos square phi. So this is what I wrote here. So this is r square sin square theta this thing. So I can rewrite this term as, so this term will be equal to, so you get here, okay, because you take r square sin square theta out, so it will be sin square phi plus cos square phi, that's equal to 1. So that means जो हमारा g of ij होगा, so the form of this metric tensor, that is equal to that er dot er, right? So that means er dot er, that's equal to 1. So that means this will be 1 0 0, and similarly for the second this will be 0 r square 0 and 0 0. So this is what, how I calculate this, the components of that metric tensor with the help of these basis vectors. And similarly, if you are interested, you can also calculate for cylindrical coordinates. तो वहाँ पे आपको क्या करना है? So you need to write here, that will be E rho, E phi and Ez. And write that cylindrical coordinates, how you write that x, y, z, right? And if you, when you write those, so you can also calculate the different components of that this metric tensor, and that can be some that 1 0 0 0 2 square 0 0 0 1. So this is very clear. Or for this rectangular coordinates, so it's very easy, right? So with the help of this, you can also calculate. So now the form of the matrix, this metric tensor is clear to us, or this is sometimes called fundamental tensor, right? Now, instead of that, so it is not right. So we are writing this. I cannot confine my this space, that Euclidean space, for 2-dimensional or 3-dimensional. I can also go for 4-dimensional also. So I can generalize that you can we can generalize it for this Euclidean space. Right? So that means I can write then our ds square will be then so this is not, it's not mandatory you can write for 3D, you can also go for 4-dimensional space. But the form of this metric tensor will be, that will be some g of u dx v. So mu nu here starts from 0 to 3. So 1 2 3 4. So this is when you are working with 4-dimensional space, right? So in the same way, so if we write now the form of the matrix, so we will see in our coming lecture. So when we discuss about that space time, now it will be quite interesting. Now we are basically making jump to physics now, right? So if our this g of ij, if g of ij is positive, now because we have this ds square dxi dx, right? So that means if g of ij is positive here, the value of this is positive, right? So ds square can be, it can be greater or equal to 0, it can be positive, negative or 0, right? So all the possible cases, right? So in that case, whenever g of ij is positive, it is called a Riemannian geometry, right? So that geometry is called a Riemannian geometry. And similarly, if you take that g of ij, if it is negative, so in that case we have right? And if g of ij is negative, and that this metric tensor is negative, so in that case our ds square, it can be positive, negative or 0 also, because ds square length element, it can be greater than 0, equal to or less than 0, right? but depends upon the value of this metric tensor. So if it is negative, so that geometry is called, that's called pseudo-Riemann geometry, right? So hope you might today it will be clear to you. So in coming lecture we will talk about that. So our next topic will be that is space-time interval in terms of these metric tensors. So if we write that space-time interval in terms of these metric tensors, so it will be quite interesting. So if you will attend these lectures, so hopefully you will get that, and thank you very much.